Welcome to the deep dive. Today we're exploring a really fascinating frontier where AI code generation meets visual design. We're looking at the research behind the JanusCoder project.
Which is this new foundational model that's really trying to bridge the huge gap between, symbolic code and what it actually looks like on screen.
It's a critical unification, isn't it?
It is. For so long, code intelligence has been almost completely focused on the text, right? The syntax, the structure.
But that's not the whole picture.
Not at all. If you think about advanced applications, maybe an interactive dashboard or generating a complex scientific plot, the code's logic is completely inseparable from how it looks.
From its visual manifestation.
The goal here was to move beyond that siloed thinking, to build one generalist interface that handles the instructions, the code, and the visual result all at once.
And that idea, unifying the symbolic logic with the perceptual visual expression, that's the core mission.
It is, and it's what you need for the really sophisticated stuff. I mean, think about the complexity involved.
You mean things like data visualizations?
Flexible data visualizations, yes. Or generating front ends you can actually edit from just a quick sketch. And maybe the toughest one, creating code-driven animations.
The paper mentioned animations for explaining concepts like attention is all you need.
That's a great example.
Yeah.
These are complex dynamic systems. So our mission for this deep dive is to really get into the mechanics.
Right. How did the researchers build this unified interface they call JanusCoder? And what kind of data engine do you even need to train a model that can span web design and physics simulation?
And that data engine, historically, that was the main roadblock. The scarcity of high-quality multimodal code data was a huge problem.
It meant models had to be specialized.
Completely. You wanted a model to turn a chart into Python code, you built a model just for that, another one for a web UI. There were all these isolated, brittle systems that couldn't generalize at all.
So JanusCoder is the attempt to solve that with a massive unified data set. Let's dig into that foundational shift then, from specialized to generalist. When we talk about these models, JanusCoder and the vision-enabled JanusCoder, what does a unified visual-programmatic interface actually let them do?
It means the model is designed from the ground up to take in different kinds of inputs.
So not just text.
Not just text. It can be text instructions, visual inputs like a screenshot, or a mix of both. And from that, it outputs high-quality executable code.
Which just blows the scope wide open compared to what came before.
It does. It establishes a kind of standard interface for tackling all these diverse, highly visual programming tasks.
Can you give us a few tangible examples? What sort of domains does this unified approach cover?
They focus on three huge areas.
Okay.
First is web UI generation and editing.
And that's more than just building a page from scratch.
Oh, much more. It includes editing existing code based on a screenshot and a simple instruction in plain English. That's a true multimodal task.
Okay, what's the second area?
Chart to code. This is all about scientific reproducibility. The model can look at an image of a complex plot.
From a research paper, maybe?
From a paper, and reproduce the exact matplotlib, Seaborn, or even R code needed to generate it.
And the third domain feels like the most complex one.
It is. That's dynamic visualizations and animation generation. This is where they bring in engines like Manim.
Which you see a lot in math explanation videos.
Right, and also Wolfram Mathematica for symbolic computation. The challenge here is you're not making a static image. You're generating code that have to evolve over time based on specific logic.
And training a single model to be good at all three of those, that's the generalist capability that was missing before.
That's the key. But that kind of synergy demands a data set that is enormous, diverse, and very, very well aligned.
So let's talk about the engine. The JanusCode 800K corpus. The scale sounds immense.
It's the foundation of the whole project. JanusCode 800K is right now the biggest multimodal code corpus of its kind. We're talking 800,000 carefully curated samples.
And it's not just big, it's balanced, right?
Almost perfectly. There's about 50.9% text-centric data and 49.1% vision-centric. And that balance is intentional. It ensures the model is just as good at interpreting an image as it is at reading code.
You don't get 800,000 high-quality samples just by, scraping the web. The paper goes into this specialized synthesis methodology. What were the core steps?
The whole process is structured in three main stages. It starts with data sourcing from public repositories.
The raw material.
The raw material. Then that moves to the second and most important stage, multi-strategy data synthesis and curation. This is where most of those 800 to 1,000 samples were actually created.
And after they create it,
They have to pass a really rigorous quality control stage. That's the final filter.
let's spend a minute on those synthesis strategies, because this is where the novelty really is. They had 4 different ways to generate these instruction code pairs. What was the first one? Guided evolution.
Think of guided evolution as a kind of iterative refinement. You don't just generate random data. You start with a known good instruction code, Paris.
Bang.
Then you use a high-level concept, like, say, add a new interactive element or change the axis to a log scale to guide the evolution of that seed.
So you're building on something that already works.
You're building complexity in a grounded, relevant way. It guarantees the new code is solvable, but also novel.
It's intelligent refinement, not just random mutation. What about the second strategy, reverse instruction? This sounds like the key to unlocking a lot of existing data.
It's incredibly effective. I mean, imagine you have huge libraries of perfectly good code-old R scripts, MATLAB routines, that never had a natural language instruction written for them.
Just raw code.
Just raw functional code. Reverse instruction uses a model to look at that code and then generate a plausible, detailed instruction that would have produced it.
So they're retroactively writing the user manual for decades of scientific code.
That's a good way to put it. They're turning these massive archives into high-quality training data. It's a really efficient way to scale up.
Very clever. What was the third strategy?
Bidirectional translation. This one is about teaching the model the abstract intent of the code, separate from the syntax.
How does that work when you're dealing with things as different as a Manam animation and a Wolfram Mathematica solver?
It's about finding the conceptual link. So if you have a Manam animation showing a proof of the Pythagorean theorem, the system captures that core idea, the geometric relationship, and translates that intent into a problem that Wolfram Mathematica can solve symbiotically.
So the model learns the concept, not just the language. It becomes domain agnostic.
It learns abstract representations that hold true no matter which programming language you're using.
And that leads to the final synthesis strategy, recontextualization. What did that add?
This one is all about depth and precision. For an existing instruction code pair, the system does a deep analysis of the code. It finds implicit logic or variable requirements, things that weren't in the original instruction.
And then it rewrites the instruction to be more accurate.
A more descriptive and precise instruction for the very same code. It tightens that semantic alignment dramatically.
So the model learns not just make a chart, but make a blue chart with time on the x-axis and a log scale.
That's the idea.
Yep.
And it enhances the quality without having to create and validate brand new code, which saves a ton of computation.
Okay, so you have these 4 powerful strategies generating 800,000 samples. But that introduces a huge risk of errors, which brings us to quality control.
Right.
What was the 2-step validation process they used to filter everything?
The first step is simple, and it's mandatory. Formal execution validation. Every single synthesized code sample has to run in a sandbox.
It has to work.
It has to execute successfully, produce a visual output, or pass its tests. If it fails, it's out. Executability is just table stakes.
But code can run perfectly and still be wrong, right?
Yeah.
It might not do what the user actually asked. What was the second step?
That's where they brought in a sophisticated reward modeling pipeline. They used a large vision language model, Qwen 2.5 VL70D, instruct to act as the judge.
So an AI judging another AI's work.
In a sense, this VLM analyzed the whole triplet, the instruction, the code, and the final visual output.
And what was it judging against? What were the metrics?
It scored each sample on 4 dimensions. First, task completion. Did it do the job? Second, solution coherence and code quality. Is the code clean and logical?
Makes sense.
Third, visual clarity. Is the output easy to understand? And finally, task relevance. Does the picture actually match the words in the instruction?
And only the samples that scored high across the board made it into the final corpus.
Only the best of the best. This multifaceted quality check is really what sets the data set apart.
Okay, so that brings us to evaluation. You can't test a model like this on simple benchmarks. They introduced a new one, DTV-Bench.
DTV-Bench, yeah. Dynamic Theorem Visualizations Benchmark. It's designed to test exactly this, creating complex, code-driven animations and proofs. It combines Manam and Wolfram Mathematica.
So how did JanusCoder do? Let's look at the performance claims, comparing the open source models to proprietary ones like GPT-4o, starting with the unimodal text-to-code tasks.
On the unimodal side, so just generating visualization code from text, the results were really striking. The JanusCoder 14b model got an incorrect code rate of just 9.7% on Pandas plot bench.
How does that compare?
That actually matched the performance of GPT-4o on the very same benchmark.
That's a huge result for an open source model. And what about generating other kinds of visual artifacts?
There, it significantly exceeded GPT-4o's performance. It shows that the diverse training data, all the web development, the theorem proofs, it all added up to a cumulative benefit.
And when you move to the multimodal tasks where vision and code intersect, how did it do on chart mimic and web page generation?
In those vision-centric domains, the JanusCoderV models consistently and substantially beat the baselines, and also outperformed GPT-4o on chart mimic.
So the data synergy strategy paid off.
It did. And in web page generation, which is where the metrics get really interesting.
On benchmarks like Design Bench and Webcode 2M.
Yes, JanusCoderV got significantly higher TreeBillU scores than proprietary models.
And TreeBillU measures what, exactly?
It's a score for structural correctness. It looks at the hierarchy of the code's document object model, the DOM tree. It's about how well organized the code is.
So it's generating cleaner, more structurally sound web code. It cares about the skeleton, not just the skin.
It shows superior structural preservation. And that's crucial for code you actually want to maintain later. It also showed strong results on the Interact Science benchmark, improving both correctness and visual alignment.
The results are clear, but the researchers need to know why it worked. What did the ablation studies show about the data synergy?
The studies really confirmed their core hypothesis. They found that data from non-target domains, even cross-modal data, provided transferable coding skills.
So the text-based data helped with the vision-based tasks.
It did. The text-centric scientific data helped improve performance on vision-centric chart generation. The diversity of the dataset wasn't just for show, it had synergistic value.
And what about that complex quality control process? Was the VLM reward model really necessary?
Oh, absolutely. When they removed that VLM-based reward modeling step in the studies, performance dropped noticeably.
Which proves that just making sure the code runs is not enough.
It is wholly insufficient. That semantic and visual alignment check from the VLM was indispensable for creating a truly high-quality corpus.
So, big picture, the data construction method itself is the key, and it works regardless of the specific model architecture.
That's the conclusion. The JanusCode 800K data gives you significant performance gains, even when you use it to fine-tune other models like Qwen3 or InternVL. The models end up with great balanced performance on general coding while excelling at these visual tasks.
So this deep dive really clarifies that the JanusCoder series is a huge step forward. It's a robust open source model that actually achieves that unified interface for code and vision. And it's all built on the largest, most carefully synthesized corpus out there today.
And what's really fascinating is what the performance metrics imply about their design philosophy. The fact that the open source JanusCoder models beat competitors on TreeBillU scores for web generation, that suggests a deliberate choice.
A choice to prioritize what?
To prioritize structural correctness. They were better at preserving the clean, DOM-level organization of the web code. And they achieved this even if it meant a small trade-off in pure, pixel-perfect visual fidelity compared to some other models. It suggests they prioritized clean, functional, maintainable code over just a perfect aesthetic copy.
That's a compelling choice. It positions the model for engineering longevity, not just a flashy demo. For those of you interested in leveraging this model, the researchers have made the code and checkpoints available on GitHub. We encourage you to explore it. Thank you for joining us on this deep dive.